Okay guys, so let's take a look at the Unit 6 review packet. Short unit, short test. It's looking to be a lot shorter than this review packet, but let's go through it together and see what we can figure out. So, as we started the unit, we did Coulomb's law. Coulomb's law is the law that tells us the magnitude of the electrostatic force between two charges. And we know the direction depends on whether they're positive or negative. So we know it depends on the sign, not the magnitude, for A. We know that an attracting force occurs when they are opposites. Opposites attract, and it depends on the sign of the charge, not how big the charge is, giving us D. We started off the unit with Coulomb's law, and Coulomb's law is made up of two relationships. How does charge affect force, and how does distance affect force? We know that as charge goes up, force goes up, making this graph A for number 3. We know that as distance goes up, however, that force actually gets smaller. Think like it's spreading out that force over a larger area, making graph 4 be D. Now, it's not just a regular inverse relationship. A regular inverse relationship would mean that in a case like number 5, when it moves from 2 centimeters to 10 centimeters apart, this increases the distance by 5, so R goes up by 5. If it were an inverse, that would make the force decrease by 5. But it's an inverse square, so it's not decreasing by 5, but 25, making my answer D. Now, the next few questions all refer to things that you should already know that were not explicitly taught in class because it's assumed that you've heard of these particles before. Like, you should pretty much be able to tell me before you take any physics class whatsoever that the electrons are negatively charged and that electrons and protons are the same magnitude of charge, even though they have different masses. So let's go through some things here. Electrons and protons both have the same magnitude of charge. That's that 1.6 times 10 to the negative 19th. But they don't have the same mass. They don't have the same mass. That's actually the reason electrons move for electrostatic simulations, because electrons are significantly lighter than protons. For the other two, protons and neutrons do have about the same mass. Their mass is both about that 1.6 times 10 to the negative 27, and those two are both heavy and inside the nucleus. Ooh, I might have given you one with 2 correct answers. So for 7, I would also say D. There's 2 false statements there. My bad. So there's 2 false statements for 7. 7 has 2 answers that are false. Both B and D. They don't have the same sign of charge. One is positive and one is negative. So, as I just mentioned, electrons are the things that move for electrostatics because they are lighter than protons and they're outside of the nucleus. So, whenever I do a simulation or look at a demonstration of electrostatics, we know that the electrons move and the protons stay stationary. Now, combing your hair is an example of charging by friction. When you charge by friction, one object becomes positively charged and the other becomes negatively charged. Now, why that would be? Think of it as if they both start as neutral. I don't know how to draw hair, person. They both start as neutral. The protons stay still, so let's draw some protons staying still. But the comb becomes positively charged. It must have lost its electrons. Electrons left the comb and went to the person the person must have gained those electrons by conservation of charge. Like, it can't have created or destroyed electrons. They just moved from one place to the other. And so your hair is negatively charged. So the picture on the right shows a charged object brought near an insulator. The insulator is an example of a polarized object. I know that it's polarized because it's neutral. See how like the negatives and positives cancel each other out? And if I draw a line down the middle, there's one side that's positive, one side that's negative, and is overall net neutral. A polarized item is an item that's neutral with charges separated from each other. Oh man, interruption. I realized that I started reading this question completely wrong and therefore answered it incorrectly and had to go back and redo this part. So, for question 11, this actually causes the metal sphere to become positively charged during this interaction. So initially, the charge was +3 on the rod and 0, but because it touches, during this interaction, electrons go from the neutral object into the positively charged object. This is a hallmark of charging by conduction. Because it touches the wand to the sphere, it therefore actually transfers charges. This does not just become polarized, it becomes charged. In this case, the 3 charge was shared over both objects, making 1, 1 and 1, 2. In this case, the sphere gains a positive charge. The sphere then has a net charge because electrons moved from the sphere into the rod. And finally, the rod and sphere repel each other because they're both positively charged. Field points from positive to negative, but specifically it points away from positive charges, so that 2 charges that are positive together would have all arrows pointing away from them. There's actually nothing that looks like D. This is actually an example of a magnetic field, so definitely not D. C is the picture of a dipole. B is the picture of 2 negative charges. So finally, multiple choice 15. When a positive charge moves in the direction of the electric field, the electrical potential energy changes. So let's just draw this out real quick. If I have a parallel plate capacitor with a positive plate and a negative plate, the electric field points to the right, from positive to negative. If I move in the direction of the electric field, the proton would move from A to B. It goes from high potential energy, because think like potential energy for an electric field is QED. The distance is decreasing. It's getting closer and closer to the plate it wants to go to. So that must mean that the potential energy is also decreasing. And just as a hint, we know potential energy decreases because the kinetic energy is increasing. As it goes from A to B, potential is decreasing because it should be getting faster. It accelerates as it goes past here. Now onto some that I'm going to explain verbally and write more details later. So, in this particular problem, Ben Franklin takes this neutral glass rod and rubber and rubbed it with a piece of fine silk. We know that before they are neutrally charged. This is an example of charging by friction. So neutrally charged to start. If the glass becomes positively charged, this means that the cloth must have become negatively charged. Charging by friction means that the protons stayed still in the rod. We'll draw them in that consistent color. We did red earlier, so we'll do red again. The proton stayed still, so its 5 electrons that it lost must have been transferred to the cloth, making the cloth -5 charged. the rod positive 5 charged? By conservation of charge. So the silk would be negatively charged if the rod was positively charged. But they both experience the same net charge. One's positive 5 and one's negative 5. If one lost electrons and the other gained it, they still have the same magnitude of charge. So, equal and opposite. 17 is another example of where polarized objects, or in this case conducted objects, are going to end up having forces between each other. So, this is an example of charging by conduction. In this case, the rod actually touches, I'm reading it wrong. Womp womp. So the charge is actually not touching the conducting sphere. So remember, protons stay still. Electrons will move because of the charge placement. Electrons want to get away from the other negative charges, making this a neutral but polarized sphere. The sphere then will actually attract because the positive charges are close and positives attract negatives. So the sphere is neutrally charged. They attract, and the charges move to the right because they're repelling. A few more electrostatic phenomenon. These have to do with the demos we did in the simulations. So, John Travoltage. Remember that in this problem, John Travoltage gained a negative charge. He rubbed his feet by charging a friction, and charging by friction made him negatively charged. That must have meant, well, if he's negatively charged John, that the carpet must have been positively charged. Then afterwards, John goes and touches the doorknob. When he touches the doorknob, he becomes grounded. The charges leave him, go to the doorknob, go into the earth, and he'll feel a shock because all the electrons will flow from his hand to the doorknob. So there's my little green electron flow arrow. Okay. Charging by conduction. There we go. That was the conduction one I was thinking of. Okay. So in this case, I have a neutral ball to start. So it has the same number of positives and negatives. When the positive rod touches the neutral sphere, some of the electrons in the sphere will transfer. That'll slightly neutralize the stick. So let's say in this case, electrons are going to flow this way. And those are going to flow until the sphere has lost 2 charges. So we're just going to flow 2 electrons over. It'll have lost 2 charges. And that would make both items positively charged. Notice the sphere is positively 2 charged now. And the rod is still positively 5 charged. They both still are positively charged as a result of conduction. Oh look, another example of polarization causing attraction. It's almost as if that's what goes on. Protons stay still inside the can. Electrons repel away from the balloon, making the can polarized. The polarized can attracts because the positive surface is left near the balloon and positives attract negatives. Ta-da! Okay. These 3 problems are all proportion problems. They require you to think of the original Coulomb's law equation. So that's K, Q1, Q2, over r squared. Then I'm going to substitute for whatever change. The distance becomes 4 times as large. So think I'm still going to keep k, q1, and q2, but I'm replacing r with 4. If I do this out, this means 1/16 of the original force remains. So this gets 16 times weaker if I bring the objects 4 times farther apart. Similarly for B, it has 3 times the charge on one object, 2 times the charge on the other object, the same distance apart. 3 times 2 is 6, so it will be 6 times the original force. Last one. So the charge on one object doubles, the charge on the other object triples, and the distance quadruples. So I'm going to do 3q1, 2q2. Distance is over 4r squared. And numerically, that leaves 3 times 2 in the numerator, 4 squared in the denominator, so 6/16. The force decreases by that fraction. So I've got one positive charge and one negative charge. This question is testing whether we can actually calculate and understand the magnitude and direction of forces. So these two are going to attract because one is positive and one is negative, and opposites attract. That means Q2 experiences a force to the left, and Q1 experiences a direction of force to the right, equal and opposite. Q1 is going to have the force kq1 q2 over r squared. So I would substitute 9 times 10 to the 9. Q1 is 3 times 10 to the negative 6th. Q2 is 9 times 10 to the negative 6th. And r is 0.2 meters squared. You may have noticed that I dropped that negative sign here. Feel free to drop the negative signs because this number tells you the magnitude, not the direction. You actually already know the direction from our earlier analysis. So this leaves a force of 6.075 newtons for charge 1. Charge 2 has to have the same amount of force, equal and opposite. So both have the same magnitude of electric force. Yes, the easy questions. Field maps. Okay, charge Q1, even if I'm not looking at the whole picture in the video right this second, charge Q1 is a negatively charged object. I know Q1 is negatively charged because the field lines point towards it. Of the 4 positions that are pictured, I'm imagining in my head some box drawn around each one. The one with the largest number of field lines nearby, the largest field density, will have the largest electric field. So I have A as the highest field, B because it has 2 field lines and those field lines are close together, C has 1 and they're a little farther apart, D is over here where there's little field. So A, B, C, D, from greatest field density to least field density, gives us the highest to lowest field. Now, what to do with the field? If I have a uniform field, then I have my positive and negative plates, and that gives an electric field that points from positive to negative. The same number everywhere in between. A proton is going to experience the highest electrical potential energy at A because that's where it's closest to the positive plate. It has the largest distance D to the negative plate. One way you could think about it is wherever it has the largest repulsion force has the largest electric potential energy. So an electron placed at E would have the largest electric potential energy for an electron placed in this field. Now, if an electron and proton are both placed at C, we actually did a homework problem like this. If they're both placed at C, then they have the same electric potential energy to start. When released from rest, that means they're going to have the same kinetic energy just before they strike the plate. But the electron will have a larger speed. It will literally be going faster because it's 10,000 times less massive. So the electron will have the higher speed because it's the same kinetic energy with less mass. You could think of this as like kinetic energy is going to be equal for a heavy object moving slowly, that's the proton, as it is for a light object moving quickly, that's the electron. The electron is faster because it has less mass. So, now let's do some mathematical analysis. We've got a positive and negative plate. I know the top plate is positive because the electric field lines are pointing from positive to negative. Done. The electron will go against the field. Its force is going upward because it wants to go to the positive charges. The force acting on the electron is going to be Q times E. I know I don't want to use the Coulomb's law equation because I don't have two charges. That just wouldn't make sense. So I'm going to take the charge of an electron from my equation sheet times the 32,000 Newton per Coulomb electric field. Notice that just like before, I dropped the negative sign here because the electric field, like this equation, tells us the direction, or the magnitude, but we already know the direction. So this leaves an electric force of 5.12 times 10 to the negative 15th newtons. And we know the direction of this force is upward. I can drop that negative sign because I already know the direction of force because electrons are attracted to positive charges. Now, at point pictured, the electron has electric potential energy. It's not currently touching any of the plates, so it'll have electric potential energy calculated by QED. I'm going to take that charge of the electron from my equation sheet, that 1.6 times 10 to the negative 19th, the 32,000 for the field, and please notice that D is not actually the one that is pictured. That is so misleading because it's the distance to the plate that is desired. In this case, D is actually 2 centimeters. But it's centimeters, not meters, guys. So when I substitute here, centimeters is 0.02 meters, making this electric potential energy that 1.02 times 10 to the negative 16 joules. And one more time, I dropped already the charge of the electron. Energies are always going to come out positive. I don't need to actually include the negative sign here. So finally, this electrical potential energy turns into kinetic energy. Just before the electron strikes the plate, all the potential energy turns to kinetic. So that means my kinetic energy is also 1.02 times 10 to the negative 16 joules. And knowing that kinetic energy is equal to 1/2 mv squared allows me to solve for speed. Careful things here, make sure that you are putting in the mass of the correct particle Lots of people put in the mass of proton for an electron, and they're not identical. So I'm doing that thing where I do some of the math out so I don't have to plug everything in my calculator at the same time. I multiply by 2 to the left and divide by 9.11 times 10 to the negative 31. This gets me 2.24 times 10 to the 14th on the left, leaving v squared on the right. Taking a square root of that value will find me the speed. Thing to note here is I could, and you'll notice I don't do this, I could just put every digit down here, but that's not a super convenient number to work with. All right, so what I might do instead, and what you see I do with my answer keys, is I tend to put everything in scientific notation. This is like 1.5 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters per second. So last page, we're almost done. The Bohr model. So if an electron orbits a proton, there must be a centripetal force acting towards the center. That force is the electrostatic force. Because the electron is attracted to the proton, the electrostatic force between them acts as the centripetal force, causing them to orbit each other. If I look at the picture of the hydrogen atom, that leaves my electric force between these two particles and the tangential velocity over here. That should look like unit 3, centripetal force, tangential velocity. If the proton were suddenly to disappear, the electron would go off along its tangential path. When it says calculate the centripetal force then, it doesn't mean go find mv squared over r. It means calculate the electrostatic force. And we can totally do that because these are two charged particles. I wouldn't use the field equation because I don't have a field, but I do absolutely have two charged particles. The electron and proton have the same charge, so I'm going to put the same number down for both. Remember, I'm dropping those negative signs because we already know they attract. I don't need to do extra math to figure out that positives attract negatives. They orbit the nucleus at a distance of 5.29 times 10 to the negative 11th meters squared. And substituting it into my calculator, we see that this leaves a super tiny force. That'll be 8.2 times 10 to the negative 8 newtons. Oh, though we already know the electron is attracted to the nucleus. Otherwise, it wouldn't orbit. So, last topic then. I've got these capacitors, and we want to figure out how to make them store as much energy as possible. It says that these plates are made of aluminum foil, so A for aluminum. If I make those aluminum plates bigger, I know that more energy can be stored. And since it's proportional directly, 3 times the area means 3 times the electric potential energy of the capacitor. Think of it as it can fit 3 times as many charges because the plates are 3 times as big. So 3 times the energy. Direct. All the words. You got it. Okay. So if 2 sheets of wax paper were placed between the sheets of aluminum foil instead of 1, that would make the distance increase by 2. And it asks how much more energy could be stored in the capacitor. Well, since that's an inverse relationship, no more energy, less energy would be stored. Half the energy would be stored because this is an inverse relationship. Less energy would be stored because it's farther apart. Finally, if if it's connected from a 9-volt battery instead of a 3-volt battery, how much energy would be stored in the capacitor? Well, this is a squared relationship. 3 times the voltage would give us 3 times the energy, but it's 3 squared. So it would store more energy. If voltage goes up, then energy goes up by V squared. All right, folks, good luck.